Approximate integration. First, why we need approximate integration. Normally, when we have a definite integral of a function, we would just use the fundamental theorem of calculus to evaluate the definite integral. However, to use the fundamental theorem of calculus, you would need to know the antiderivative of the function involved. And we do not know the antiderivative of e to the x squared, nor do we know the antiderivative of the square root of 1 plus x cubed. And when I say we don't know it, I mean we don't know it. It is an unknown antiderivative. None of the methods that we have learned up to this point allow us to find the antiderivative of these functions. But we still want to be able to calculate these definite integrals, since these represent the area under these curves, and finding the area, or at least approximating the area, is very important in some applications. The first method of approximating integrals is the midpoint rule. And we actually talked about this rule in an earlier video lesson. This tells us that if we want to calculate the area under a curve, or a definite integral, we are going to use a finite number of rectangles defined on that interval, where the height of the rectangle is given by plugging the midpoint of each of these subintervals into the function involved. So in this case, when you add up the areas of these rectangles, you're going to take the height of the first rectangle multiplied by the width of the first rectangle, plus the height of the second rectangle multiplied by the width of the second rectangle, etc. And we do this all the way up to the last rectangle, which I will call the nth rectangle. And you can see that in this case here, you can factor out a delta x. And when you do that, you simply get f of x1 bar plus f of x2 bar plus all the way up to f of xn bar. And the f of xi bar is just the function value at the midpoint of that corresponding interval, as you can see down below here. So that is where this formula comes from. Delta x, of course, is b minus a divided by n. And here we have a formula for finding the midpoint of a particular interval. Normally, you can find the midpoint in a much more intuitive way, and we'll talk about that in our first example. The next method for approximating definite integrals is called the trapezoidal rule. The trapezoidal rule is very similar to the midpoint rule, except that now when I want to approximate the area under a curve, instead of using a rectangle to approximate that area, I'm going to use a trapezoid. So let's zoom in here a little bit. Notice that this shape here is a trapezoid. A trapezoid is a four-sided polygon where two sides are parallel, but the other two sides are not necessarily parallel. And you can see that the area of this trapezoid is very close to the area under the curve. It just misses a small amount of area here. And so if we do this for all of the subintervals, this will give us a reasonable approximation to the area under the curve. So now, where does this formula come from? Well, let's look at the area of the first two trapezoids. And to talk about that, we might need to review the area of a trapezoid in the first place. Suppose we wish to find the area of this trapezoid, where one of the parallel sides has a length of b, the other one has a length of a, and then the distance between those two parallel sides is h. And we often call this h because if you turn this on its side, this h would represent the height of the trapezoid. The area formula for a trapezoid is 1/2 times the height times the sum of the bases. So it's 1/2 h times a plus b. Now, if you go to the trapezoids that we have here, you can see for the first trapezoid, which I'm just going to call T1, one of the bases is this value, and that is simply f of x0, right? That's this length here. And the other base is this value, which is f of x1. And then the distance between x0 and x1 is what we call delta x. And so the area of that first trapezoid, which I'm going to call T1, is going to be 1/2 times delta x times f of x0 plus f of x1. Now what about the area of the next trapezoid? So we'll call this area T2. Well, one of the lengths of the bases is still right here. That's f of x1. So notice that f of x1 is a base of the first trapezoid, and it's also a base of the second trapezoid. And then the other base of the second trapezoid is this length here, which is f of x2. And of course, the distance between these is still delta x. So the area of the second trapezoid is 1/2 times delta x times f of x1 plus f of x2. And we repeat this process. So the area of the third trapezoid is going to be 1/2 delta x, f of x2 plus f of x3, etc. And when you get to the last one, it's going to be 1/2 delta x times f of xn minus 1 plus f of xn. Now, when you add all of these together, what's going to happen is every one of these function values gets added twice. So f of x1, f of x2, f of x3, etc. They all get added twice except for the very first one and the very last one. And that's because those lengths are only involved with one trapezoid. So when you look at the formula up here for the approximate area under the curve using trapezoids, what you'll see is delta x divided by 2, and that's just the 1/2 delta x that has been factored out of everything. And then you have all of the function values where the first one and the last one occur only once, meaning that there is a number 1 in front of these. But all the other ones occur twice because each of the other function values involved are a base of 2 trapezoids. So that is where this formula comes from. So now let's go ahead and do an example where we approximate the area under a curve using the midpoint and trapezoidal rules. In our first example, we want to first use the trapezoidal rule with n equals 5 to approximate the integral from 1 to 2 of the function 1 over x dx. So first, let's just identify that our function here is the function 1 over x. And to your right here, I have a graph of the function 1 over x on the interval from 1 to 2. You don't have to draw a graph of the function with the trapezoids. All you really need to do is look at the number line, but I have a graph here for your reference. First thing we want to do is calculate delta x. We know that delta x is b minus a divided by n. In this case, that's 2 minus 1 divided by 5, which is 1/5, or in decimal form, it's 0.2. So what that means is we now know how to find the rest of these endpoints. So from 1, I'm going to go 0.2 units to the right, and that's going to give me 1.2. Another 0.2 units to the right gives me 1.4, and then 1.6, 1.8, and finally 2. Now, these are the numbers that we're going to use when we use the trapezoidal rule. So let's remember that the trapezoidal rule tells us that the integral here is approximately delta x divided by 2 times f of x0 plus 2 times f of x1 plus 2 times f of x2 plus 2 times f of x3 plus 2 times f of x4 plus finally f of x5. So now we just need to identify what is x0, x1, x2, etc. Well, again, that's just these endpoints here. So for us, we are going to have delta x, which is 0.2, divided by 2. And then we'll have f of 1 plus 2 times f of 1.2 plus 2 times f of 1.4 plus 2 times f of 1.6 plus 2 times f of 1.8 plus finally f of 2. So now we just need to do some approximating here. First, let's just go ahead and say that 0.2 divided by 2 is 0.1. Now, what is f of 1? Well, remember, your function is 1 over x. So f of 1 is going to be 1 divided by 1. Plus, then we have 2 times f of 1.2. f of 1.2 is 1 divided by 1.2. Plus 2 times f of 1.4 is 1 divided by 1.4, etc. Oops. And then f of 2 is just 1 divided by 2. And now we're just going to plug all of that into a calculator, and let's give a 6 decimal place approximation. And this is approximately 0.695635. Now the question is, how good is this approximation? Well, we know the actual value of this integral can be found by simply using the fundamental theorem of calculus. So you know the antiderivative of 1 over x is the natural log of the absolute value of x, and this is on the interval from 1 to 2. And so this ends up being the natural log of the absolute value of 2 minus the natural log of the absolute value of 1. Natural log of 1 is 0, and then the natural log of 2, if you plug that into a calculator, is 0.693147. So that's the actual value of the integral. The value that we got was this value here. So we can calculate the error. And to get the error, you would simply take the approximated value minus the actual value. And so in this case, that is 0.695635, and we're going to subtract 0.693147. And this is approximately 0.002488. And sometimes we don't actually care about the error as much as we care about the absolute value of the error. And so in that case, it would just ensure that this number comes out to be a positive number. In any case, we can see that our answer is pretty close to the actual value. Now, of course, I should say that in this problem, it would really not make any sense to use this method for finding the area because we know the actual area, right? And doing this is easier. So this method is really going to be used for functions that we don't know how to integrate or that are very difficult to integrate. So the main point of this example is to do a problem that we actually can do using the fundamental theorem of calculus so that you can see how good this approximation really is. And mind you, we only used n equals 5. The higher n is in the problem, the greater this number is, the better the approximation gets. So now let's go ahead and use the midpoint rule to approximate the same integral. So of course the function is the same. We still have the function f of x is equal to 1 over x. Delta x is also still the same. It's b minus a divided by n, which is 2 minus 1 divided by 5, which is 0.2. All of these endpoints here are going to be the same. So 1.2, 1.4, 1.6, and 1.8. But when you use the midpoint rule, you have to find the midpoints of each of these intervals. And so we just have to find the number that is between these endpoints. Now in this case, I think this is fairly intuitive. I think we all know that the number halfway in between 1 and 1.2 is 1.1. The number halfway in between 1.2 and 1.4 is 1.3, and so on and so forth. Now, I will just mention that if you don't know how to get these midpoints, then you can use the formula. So, for example, to find the midpoint here, all I would have to do is take the endpoints, 1.2 and 1.4, add those together and divide by 2, and that's how we get 1.3. Okay, so now let's go ahead and apply the midpoint formula. The midpoint formula is a little bit simpler. It is going to be delta x times f of the first midpoint plus f of the second midpoint plus f of the third midpoint plus f of the fourth midpoint, and finally plus f of the fifth midpoint. And that is because n is equal to 5. So now delta x is 0.2. We're going to have f of 1.1 plus f of 1.3 plus f of 1.5 plus f of 1.7, and finally plus f of 1.9. And now we just need to plug all of those into our function. Our function is 1 divided by x. So f of 1.1 is 1 divided by 1.1 plus 1 divided by 1.3 plus 1 divided by 1.5 plus 1 divided by 1.7 plus 1 divided by 1.9. And now from here, we're just going to plug this into a calculator to get a 6 decimal place approximation. And this value is 0.691908. Now again, if I want to take a look at the absolute value of the error involved here, I'm going to take the absolute value of the approximated value minus the actual value. And in this case, that is going to be the absolute value of 0.691908 minus, and then remember the actual value was the natural log of 2. And if I plug this into a calculator, I get 0.001239. And you might notice that the error when using the midpoint rule is a little bit less than the error when we used the trapezoidal rule. In fact, the error is about half. We'll talk about why that is in just a moment. And again, I just want to emphasize that if you know the actual value of the integral, there's no reason to use approximate integration. So think about that. The only time you would use approximate integration is when you don't know this value. And so you're never going to know what your actual error is, because if you knew your actual error, you would know the precise value and you wouldn't have to approximate in the first place. So really the question comes down to, how do we know how good our approximation is, even when we don't know the actual value of the integral? So we're going to talk about how you can measure the bounds on the error. So we have two formulas. The first formula here says that if you want to find the error when using the trapezoidal rule, it will be no more than k times b minus a to the third power divided by 12n squared. Now k is the maximum value of the second derivative on the interval. And the error when using the midpoint rule is going to be the same exact thing, except that instead of the number 12, we have the number 24. So the first question here regarding error says, how large should we take n in order to guarantee that the trapezoidal and midpoint rule approximations for the integral of 1 over x from 1 to 2 dx are accurate to within 0.0001. Okay, so what this means is that we want the absolute value of our error to be less than 0.0001. Now, what do we know about our problem? Well, again, it's the integral from 1 to 2 of the function 1 over x dx. So the function is 1 over x. A is equal to 1, B is equal to 2, and we don't know the value of n. In fact, the value of n is what we're looking for. We also don't know the value of k, and k is something that we must have to be able to approximate this error. So k comes from looking at the second derivative and asking, how large can the second derivative be on your interval? So let's go ahead and talk about the second derivative. Now, our original function is 1 over x, which is x to the negative 1. So the first derivative is going to be negative 1 x to the negative 2. And our second derivative is going to be negative 2 times negative 1, which is 2 x to the negative 3. And that is the same as 2 divided by x cubed. So if I look at the absolute value of the second derivative, that would be the absolute value of 2 divided by x cubed. And we need this to be less than or equal to k for some k value. So when you get to this point, basically the question is this: how big can this expression get on the interval? And the interval in question here is from x equals 1 to x equals 2. Well, if you think about it, when you have the number 2 divided by x to the third power, this is going to be the largest when the bottom is the smallest. So 2 divided by x cubed for all of these values of x is going to be the smallest when x is equal to 1. So the value of k is going to be the absolute value of 2 divided by 1 cubed, which of course is just 2. So now that we know the value of k, the value of a and b, and we know that we want our error to be no more than 0.0001, let's think about how we can figure out what n is. So we know the absolute value of our error here is going to be less than or equal to k times b minus a to the third power divided by 12n squared. And we need that to be less than 0.0001. So if I fill in the value of k is equal to 2, the value of b equals 2, a equals 1. And then on the other side, I'm going to change this to be 1 divided by 10,000. We should now be able to solve for n. So what I've got here is 2 minus 1, which is 1. 1 to the third power is 1, times 2 is 2. So that's going to be 2 divided by 12n squared is less than 1 divided by 10,000. Now I can cancel 2 goes into 12 6 times, and we have 1 divided by 6n squared is less than 1 over 10,000. Now a little trick that you can do here is you can multiply when you have an inequality with two positive numbers. You can multiply the bottom number up to the top here, the bottom number up to the top here, and when you do that, the inequality stays facing the same direction. So 1 times 10,000 is 10,000, and 6n squared times 1 is 6n squared. And now if I divide by 6, I end up getting n squared is greater than 10,000 divided by 6, which of course I could reduce, but instead I'm just going to go ahead and take the square root of both sides. And from here we get n must be bigger than the square root of 10,000 divided by 6. And if you plug this into a calculator, you will find that this is approximately 40.8. So the minimum value that I need to use to ensure that the error is no bigger than 0.0001 is 41, right? N must be bigger than 40.8. N is the number of subintervals, so it has to be a whole number. So we have to take the first whole number that is bigger than 40.8, and that is 41. Now let's talk about how large n should be if we're using the midpoint rule. Now everything else is exactly the same, except that when you're using the midpoint rule, this number down here is 24 instead of 12. So let's go ahead and make that change. And so when we do that, and we're going to go ahead and plug everything in just like before. On the left-hand side, we end up with 1 over 12n squared. On the right-hand side, we have 1 over 10,000. If we cross multiply, we get 10,000 must be less than 12n squared. Dividing both sides by 12, we will end up with n squared must be bigger than 10,000 over 12. And finally, taking the square root of both sides, we get n must be larger than the square root of 10,000 divided by 12. And this number is approximately 28.9. So if we take the first whole number larger than 28.9, we get 29. So if using the midpoint rule, we would have to use at least n equals 29 to guarantee that our error would be less than 0.0001. In our next example, we want to use the midpoint rule with n equals 10 to approximate the integral from 0 to 1 of the function e to the x squared dx. Notice that we do not know the antiderivative of e to the x squared. So this is the first time we really need an approximate integration formula to be able to do this. So what I'm going to do is set up a number line from 0 to 1, and I'll compute delta x. Delta x in this case is b minus a divided by n, which of course is 1/10 or 0.1. And if I divide up this number line into 10 equal parts, you can see that the endpoints of your intervals are going to be 0.1, 0.2, 0.3, 0.4, etc., all the way up to 1. Now, we need the midpoints. The midpoint of this first subinterval is going to be 0.05. The midpoint of the second interval here is 0.15, and then 0.25, 0.35, 0.45, etc. And now the midpoint formula says that this integral will be approximately delta x times f of x1 bar plus f of x2 bar plus all the way up to f of x10 bar. Now this is going to be a pretty tedious process. Delta x is 0.1. F of x1 bar is going to be f of 0.05 plus f of x2 bar is going to be f of 0.15 plus f of the next one is 0.25, etc., all the way up to f of 0.95. And now what you have to do is take each of these values and plug it into the function e to the x squared. And when you do that, this is what that's going to look like. And so just for clarity here, when you plug in 0.05, you're going to have e to the 0.05 squared, but 0.05 squared turns out to be 0.0025. So I took the liberty here to do the squaring and just showing these results. But when you plug this into the calculator, you're going to get approximately 1.460393. Now the second part of this question is, give an upper bound for the error involved. In other words, how good is this estimate? What is the maximum error involved with doing this? So to do this, we need the formula. So we know that the error involved here for the midpoint rule is going to be k times b minus a to the third power divided by 24n squared. And we actually know that the error is going to be less than or equal to that. So we need to find our value of k. K is going to be greater than or equal to the second derivative on the interval from a to b. So we need to first find what is our second derivative. So f of x is e to the x squared. The first derivative is going to be e to the x squared times the derivative of x squared, which is 2x. And the second derivative, we have to use a product rule. So 2x times the derivative of e to the x squared plus the derivative of 2x times e to the x squared. And this is going to be 2x times 2x e to the x squared plus 2 times e to the x squared. And this is 4x squared e to the x squared plus 2e to the x squared. And if we factor out an e to the x squared, we get e to the x squared times 4x squared plus 2. Okay, so how big can this get? What is the absolute value of this second derivative? Well, it's going to be the absolute value of e to the x squared times 4x squared plus 2. And the absolute value of the product of two things is equal to the absolute value of the first thing in absolute times, the absolute value of the second thing. So now the question is, how big can each one of these get on the interval from 0 to 1? Well, in this case, e to the x squared will be its largest when x equals 1. And 4x squared plus 2 will be its largest when x equals 1. So if I plug in 1 here and if I plug in 1 here, the biggest this is going to be is going to be e to the 1 times absolute value of 4 plus 2. And this is basically 6e. So I know that the absolute value of my second derivative will never be bigger than 6e. So this is going to be my value of k. So when I come back up here, we have the absolute value of our error must be less than or equal to 6e times b minus a is 1 minus 0 to the third power divided by 24n squared. And n, of course, is 10. So let's just go ahead and plug in 10 squared there. And now I just need to calculate how big is this. Well, on top we have 6e, and in the bottom we have 24 times 100, which is 2400. And this is e divided by 400. And e divided by 400 is 0.0068. So we know that the value that we found earlier is no more than this far away from the actual value. Now let's talk about Simpson's rule. Simpson's rule is yet another formula for approximating the error under a curve. And you'll notice the formula is a little bit more complicated than the previous two formulas. Here's a basic description of what's happening. Suppose you have some function that you're trying to find the area under. What you're going to do is you're going to use parabolas to estimate the area under the curve. So for example, if you look at the function f of x here that goes through these 3 points, we can find a parabola, a unique parabola that goes through those same 3 points, and the area under that parabola is approximately the same as the area under that curve. Same thing here. We have our function. We take 3 points. We find the parabola that goes through those 3 points, and the area under that parabola is very close to the area under the curve. Now, why would we do this? Well, in the midpoint rule and the trapezoidal rule, you end up approximating the area under a curve with straight figures like trapezoids and rectangles. Here you are approximating a curve with a curve. So what happens with Simpson's rule is the approximation is much better. All right, so you have to memorize this formula here. It's not that hard to memorize. What you need to do is think of the pattern. So it's delta x divided by 3. It's f of x naught plus 4 times f of the next value plus 2 times f of the next value, and then 4 times f of the next value. So the pattern is it goes 1, 4, 2, 4, 2, 4, and then 1 at the end. Okay, so if you're a little bit lost of what I'm talking about here, remember back to the trapezoid formula where we had a 1 in the beginning and a 1 at the end, and all the ones in the middle had 2's in front of them. Well, Simpson's rule has a pattern of alternating between 4 and 2, but it starts with a 4 and it ends with a 4. And the other thing that must be true for this to work is n has to be even. Okay, so the number of subintervals has to be an even number, like, for example, n equals 6, like you can see here. Let's take a look at an example. Let's use Simpson's rule with n equals 10 to approximate the integral from 1 to 2 of 1 over x dx. And so this is the same integral that we approximated earlier. So let's just take note of the fact that f of x is 1 over x. We are on the interval from 1 to 2. So that means a equals 1, b equals 2. N, they told us, is 10. And so delta x is b minus a divided by n, which is 0.1. Now, when I do this using Simpson's rule, I'm going to take my interval from 1 to 2, and I'm going to divide this up into 10 equal parts. We'll find each of the endpoints of the subintervals, and all of this work is identical to the work that I've previously described, which is why I'm not giving a lot of instruction here. And then now, to approximate the area under the curve, the formula says that it's delta x divided by 3 multiplied by, and it's going to be f of 1 plus 4 times f of 1.1 plus 2 times f of 1.2 plus 4 times f of 1.3, etc. And it alternates back and forth until you get to the second to last number, which again is going to be 4 f of that number plus f of the final number, in this case f of 2. And so now all we have to do is plug all these numbers into our function and do the corresponding math. And of course, delta x we know is 0.1, so I can go ahead and plug that in here. Let's go ahead and plug this into a calculator to see what we get. All right, so when you do the math here, you can see that you get approximately 0.693150. This is a much better estimate than the estimates that we had earlier using the trapezoid and midpoint rules. So the second part, actually there is no second part, excuse me, but let's just go ahead and calculate what that actual error is. So we know that the absolute value of the error here is going to be the approximated value, 0.693150, minus the actual value, remember, was the natural log of 2. And if you plug this in on a calculator, you get 0.000003. So you can see it has a very small error associated with it. So this is a much better approximation. Now for the error formula, when using Simpson's rule, you'll notice that it's very similar to the formulas for the trapezoidal and midpoint rules, except that now k is the maximum value of the fourth derivative, and in the denominator you have 180 into the fourth instead of 12n squared or 24n squared. So let's take a look at this next example. How large should we take n to be to guarantee that Simpson's rule approximation for the integral that we just looked at is accurate to within 0.0001? So again, first thing I'm going to do here is write down my function as 1 over x, which is x to the negative 1. To figure out the value of k, I need the fourth derivative. So let's go ahead and start taking some derivatives here. Here's the first derivative. There's the second derivative. Here is the third derivative. And finally, the fourth derivative is 24x to the negative 5. So the absolute value of the fourth derivative is going to be the absolute value of 24 over x to the fifth power. And we need to know how big can this get on the interval from 1 to 2. Well, again, it's going to be its largest when you plug in x equals 1. So if I plug in 1, I get 24 divided by 1 to the fifth. This is my value of k. And so k is 24. All right, so now we know that k times b minus a to the 5th power divided by 180 into the 4th. This is the maximum value of the absolute value of our error. We need this to be less than 0.0001. And now we're just going to substitute k is 24, b is 2, a is 1, 0.0001 is 1 over 10,000. And now I'll just do the math here. 2 minus 1 is 1 to the 5th power is 1. 24 divided by 180 into the 4th. You can simplify that. This is going to be 2 over 15 into the 4th, less than 1 over 10,000. Cross multiplying, we have 20,000 less than 15 into the 4th. Next, we divide by 15. This is going to give us n to the 4th power is greater than 20,000 divided by 15. And finally, we will take the 4th root of both sides. That will allow us to solve for n. And the 4th root of 20,000 divided by 15 is 6.04. And so we need to take n to be the first whole even number bigger than 6.04. And that means n must be 8. So remember, for Simpson's rule, n must be even. And that concludes this video lesson.